So what we're going to talk about today is simple harmonic motion. And we're just going to constrain it to everything we need to know for the AP exam. So first off, what is simple harmonic motion? So I want to give a couple other words just so that we understand exactly what's going on. Well, the first word I want to come up with is periodic. A periodic motion is anything where the motion repeats in a very finite time interval, in a consistent finite time interval, right? So that's a periodic sound. It is not simple harmonic motion. Although simple harmonic motions are periodic, all things that are periodic are not simple harmonic motions. An example of something that is periodic but not simple harmonic is if I bounce a ball, and let's pretend that the collision with the floor is perfectly elastic so that it bounces back up to the same height over and over and over, bum, 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 that's going to take a very specific amount of time each time that you go through it, one after the other, but it would not be simple harmonic motion. It is periodic motion. So let's add on the harmonic piece to it. So for a motion to be harmonic, it has to have one very specific idea. So the reason why this ball is going down towards the floor is that there is a force of gravity downwards on it. Now, the thing about the force of gravity is the Fg here is consistent and it is downwards. So the Fg is not a function of time or position or anything. So the force that's bringing this to the bottom point, and by the way, let's call this point what it is. This point would be a stable equilibrium. So what is a stable equilibrium point? That is where the u as a function of x is a minimum, or u as a function of y, u as a function of whatever position variable is a minimum, right? So if I'm talking about a potential energy graph, we would want any simple harmonic motion or periodic motion to be a motion about a stable equilibrium point. So what does it mean to be harmonic then? What it means to be harmonic then is that that force that is bringing the object to the stable equilibrium point has to be a function of the distance from the stable equilibrium point, right? So I'm going to call this force that is bringing things to the stable equilibrium point a restoring force. So simple harmonic motion is very much about a restoring force, that there has to be a restoring force. And that restoring force, which I will call F restore for, it has to be a function of x, where x is the position with respect to the equilibrium, that stable equilibrium. Because the force of gravity here is constant, it's not a function of its height from the stable equilibrium. It's not harmonic. It's merely periodic. Then, if I want a simple harmonic motion, what has to be true is that this restoring force needs to be a direct relationship with the position with respect for equilibrium, right? So a direct relationship with the position from equilibrium. So if the restoring force had a squared relationship with that position, then it wouldn't be simple harmonic motion, it'd be harmonic motion, right? So there you go. So a simple harmonic motion is periodic. It's harmonic because the force that's bringing it to the stable equilibrium position is a function of that position with respect to the equilibrium. And then it is simple because it is a direct relationship. So that's the definition of a simple harmonic motion. So let's talk about the simplest simple harmonic motion. We're going to call something called the simple harmonic oscillator, right? Or SHO, SHO for short. The simple harmonic oscillator is a point mass on a massless spring. Okay. So that's going to be what this is, a point mass on a massless spring. So I'm going to draw my point mass as a box just because it's easier to draw in a lot of ways. And here we go. So if I have a mass on the end of a spring, so here's my spring, here's my mass. Let's say that this is the equilibrium position for the spring, because let's remember the spring force is equal to negative kx, where x by definition is the position with respect to the equilibrium position. right? Very specifically with respect to the natural length of the spring. So this is where our x is equal to 0. And so what happens here is if I move this artificially to the right here, and let's say to the right is positive, and so I move it to some sort of position x initial, right? So here x equals x initial, positive x initial. We know that the spring force is going to move this back in this direction. And because the spring force is a function of the position, this thing is going to be in harmonic motion because the spring force has a linear relationship with that position from the equilibrium position. It is going to be a simple harmonic motion. So the mass on the end of a spring is a simple harmonic motion. Now, let's make this floor frictionless just to make this nice and simple. We'll talk very briefly about what happens if there is friction. So what happens when this is your motion? Well, what we know is that this object is going to move back towards that position here. We know when it's in this position, it is going to have no spring force here, but it's going to have a velocity in that direction. And we know then it's going to continue onwards and compress the spring until some point when it stops, right? And we know that when it stops, and I'll prove this, is it stops at x equals negative x initial there, right? And this is the velocity is equal to 0. And then it's going to move its way back to this position, except that when it goes back to this position, then it is going to now have a velocity to the right, boom. And those two velocities are going to be the same magnitude, the same speed, and then it's going to go back to this position and oscillate back and forth, back and forth. Now, so as we talk about this, what is happening as the object goes from here to here? Well, it's important to realize that the size or the magnitude of the spring force is decreasing as x decreases, because that's that direct relationship that we were talking about. But what is happening simultaneously here is if the force is decreasing, that means that the acceleration is going to decrease as well. And we'll look at that in just a minute. But even though the acceleration is decreasing, the velocity here is going to be increasing. The speed of this thing is going to be increasing as it speeds up. So since these are an opposite, we're going to have a speed that is increasing, but is going to increase decreasingly. Okay, and then here, it's going to slow down. So the speed is going to decrease, but it's going to do so increasingly as the acceleration, when we're in this direction, every time I'm to the left of the equilibrium position, the spring force is going to be to the right. So this is going to speed up decreasingly, slow down increasingly, speed up decreasingly, slow down increasingly, and back and forth. And so what we hope to see here is that we have non-constant accelerations, non-constant speeds, non-constant positions as this thing oscillates back and forth. That's what's going on. That's why simple harmonic motion requires calculus in order to understand, is because that changing acceleration. So let's look at it. So we said to the right was positive. So I'm going to do a sum of forces in the x direction is equal to ma. And so that's going to be the spring force is equal to ma. And you won't have to do these derivations because it's going to be multiple choice, but there's a couple of important things to note. For the simple harmonic oscillator, then we got negative kx is equal to ma. And therefore I'm going to have the following. Negative k over mx is equal to a. So right there, we have proven that this is simple harmonic motion. Why? Because the acceleration is directly proportional to the displacement from equilibrium. And even more importantly, this negative sign, that means that that restoring force is always acting inwards towards that stable equilibrium, right? This object is always going to accelerate towards a stable equilibrium. When it's to the right of the stable equilibrium, that means the acceleration is pointing to the left. And when it's to the left of the equilibrium, that negative sign that we would plug in there would make this a positive, meaning it's accelerating towards the right. So this idea here, that acceleration is directly proportional to the negative something displacement, this is the characteristic equation of simple harmonic motion. And we'll talk about what goes in here. In this case, what goes in here is k over m. But acceleration being directly proportional, actually in this case we could just say is equal to the negative position with respect to the equilibrium, on some sort of constant there, because K is the spring constant, M is the mass, that's a constant. There you go. So that's going to be super important. So looking at this, though, this would be really hard to solve, right? Because if I do substitute, separate, and integrate here, folks, if I did dv dt is equal to negative k over mx, I've got these t's, x's, doesn't work. But if I do d squared x, dt squared is equal to negative k over mx. Now I have a second order differential equation. Now we did this early in the year, so this is something to know. By the way, you should know that the simple harmonic oscillator, or this every simple harmonic motion, ends up with one of these second order differential equations, and so you should know their format. Notice I have the second derivative of some position function with respect to time is equal to negative some constant times whatever that same position variable is, right? So this is a constant, this is position, and this is position. This could be y's, this could be z's, this could be thetas, this could be r's, it could be anything as long as the same position variable here and here. And that's just something to know about simple harmonic motion. But what does this end up being? Well, we actually looked at the solution for this earlier. Since this is a video just about knowing things for the AP exam, I'm not going to do the derivation. What we find out then is that x as a function of t is equal to, well, I know that this thing is oscillating back and forth, so it should be no shock that what I end up with is a trig function. In this case, it's going to be a cosine, because if I'm starting here, I'm starting not at the equilibrium position, so cosine starts at the top, and then this distance here, this initial distance from the equilibrium, you could call that x initial, but instead what we're going to call it is we're going to call it the amplitude, or capital A. So this ends up being amplitude cosine of something. Now we know the something there has to be a function of t. So what we're going to see here is what would this be is in order to make this equation work, in this case, it would have to be the square root of k over m t plus phi. Now, phi is going to be something that we are going to call the phase angle. Okay. And that if I took the derivative of this twice, we would find out that this is equal to negative k over mt. You would have that in there, and it would work out pretty easily. Phase angle is just a constant, right? We'll talk about what that means. In this case, at t equals 0, right, this term zeroes out, I would need, if this is my simple harmonic motion, I would need the x position to be a, meaning the phase angle is 0. But let's say if I wanted to start the thing here, if I opened my eyes and it was already moving and it was at this position, the phase angle wouldn't be 0. It's a way of just shifting the motion, the starting position of the motion around. So the phase angle is about the initial position in the cycle. So the rest of this that I'm going to do, I'm just going to say the phase angle is 0. We're going to start it at the end and then move it back and forth. But I could very easily write this in terms of signs or whatnot. So there we go. And if I take the derivative of that, I would get a radical k over m negative sine of radical k over mt plus phi. If I took the derivative of that again, I would get negative a k over m cosine of radical k over mt plus phi. There we go. And those would be the equations of motion for something that is the simple harmonic oscillator. So that radical k over m term is kind of interesting because there's that term there. So we're going to try and find out what that is. Well, so when looking at this then, well, what is the thing in a cosine that goes in front of the argument of the cosine? So if I say cosine of x, cosine of 2x, cosine of 3x, hopefully you'll remember that the thing in front of the argument is the frequency. So that's what this is here. It is something called the angular frequency of the oscillation. And so I'm going to define that. Angular frequency. Angular frequency is going to be omega. Now you're going to say to me, hold on a second, that is angular speed from the last unit. We're going to see a connection there in a couple of minutes. So for a simple harmonic oscillator, the angular frequency is radical k over m, meaning I can rewrite this equation that A is equal to negative omega squared x. And this is actually the characteristic equation of simple harmonic motion. All simple harmonic motions have to come into that where the omega is unique to the specific physical parameters that you have. All right, so what does that mean? Well, angular frequency, we've looked at that before. That is 2 pi over the period, right? It's also 2 pi times the linear frequency, meaning the period of a simple harmonic oscillator is just going to be 2 pi over omega, or 2 pi radical, and because this is in the denominator, I flip it around, m over k. And so if you think about it, that should make sense, that the larger the mass on that spring is, the longer it's going to take to go back and forth. The more pull that spring has, the greater, the faster it's going to go back and forth. All right, all that makes a lot of sense. Let's revisit this from another perspective, which is energy. So going back to this, if I call this position 1, this position 2, this position 3, if I talk about the energy of this object in position 1, well, that's going to be entirely potential energy due to a spring. So that's 1/2 kx squared, but I know when I'm at the max position there that x is the amplitude. So there it is. And at position 2, I know that it's entirely kinetic energy. So that's going to be 1/2 m v com squared, right? Okay, and so then I know that E1 is equal to E2 because the work non-conservative is 0. That means that's because there's no friction there, and the spring force is a conservative force, so I can do that. So 1/2 Ka squared is equal to 1/2 mv, in this case max squared. The halves go away, and if you look at this, if I take the square root, then V max is equal to A times radical K over M. Yes? So if you look then to our equations here, V max is equal to, and by the way, that was the speed, right? Because that should be plus or minus, because I did take the square root. A radical K over M, and then the max value of this is 1 or negative 1, so that can form. So conservation of energy gave us that same thing. So V max is equal to A radical K over M. So we might as well look at A max then. So if I look here, what is going to be the max value then of this function? It's just going to be the amplitude K over M, okay? And so those are nice little simple equations that we can use to solve a lot of multiple choice questions, right? So even though A is going to go between plus or minus this value, that's its maximum value. So notice here, the max values of these things are based on the amplitude, but the period of motion is not based on the amplitude there, right? That's because for higher initial displacements, the V max is higher. So even though you're traversing across a larger amount of space, it doesn't take more time because that higher maximum speed sort of like, kind of gets you there. So there you go. So there you have your simple harmonic oscillator. And if I wanted to talk about some point, let's say position 3, well, that's when it's back out at its other position. And we know that that's also going to be 1/2 kx squared. Oh, and since these two have to be equal to each other, that's how I know that's going to go back out as far from the equilibrium position that it was the other direction, because that and that have to be the same. So when I come back over here, that's how I can prove that here. In this case, x at position 3 has to be equal to negative A. It has to be because of the conservation of energy. But if I wanted to look at some intermediary place at any given point, the total energy has to equal 1/2 kx squared plus 1/2 mv squared. And so there you go. And I know that the best way then to find the energy of the simple harmonic oscillator is just to use what has to be the total energy, which is 1/2 k times the amplitude squared, since amplitude is defined as the maximum position that this thing gets away from equilibrium. And this term would drop to 0 when you're at that position. So this is the total energy of the simple harmonic oscillator, the nice and simplest way to find it. So that's what we have for the simple harmonic oscillator. Now, So just to then recapture, in general, simple harmonic motion is going to have the following equations. Right, which are called the characteristic equations of simple harmonic motion. And then we can then say, specifically for the simple harmonic oscillator, we have found using the sum of force equation that omega is radical k over m for that particular motion, which means the period of the simple harmonic oscillator is 2 pi radical m over k. That all these equations, I could put the omega, the radical k over m there. I know that P max is equal to plus or minus a radical k over m. A max is equal to plus or minus a k over m, and that E total is equal to 1/2 k a squared. So those are true for the simple harmonic oscillator, the mass on the spring. Now, I will say that this is the same for the mass on a spring this way, as well as if I were to hang it, right? So the only difference about the hanging simple harmonic oscillator is that the equilibrium position for the spring is not the same as the equilibrium position about which this thing oscillates, because we know that this thing is going to come to rest and it's going to oscillate about some sort of middle position here, right? And it's going to oscillate back and forth between those positions, right? So here, if I call that y is equal to 0, what is this distance? Well, here, that's got to be the equilibrium position, the stable equilibrium. So it's got to be where the acceleration is equal to 0. And that's going to be where the spring force is equal to the force of gravity. And so if I plugged in both of those, that would happen at a position x is equal to mg over k, meaning that this distance here is mg over k, and this distance is mg over k. But the important thing here is, when I'm looking at these equations, this position x, this is kind of confusing here because I wrote x equals to 0. This x would be actually for, in the spring force, negative kx, where x here has to be a function from the natural length of the spring. But if I'm talking about the simple harmonic motion in this case, I would write these in terms of y, because I would need this thing to oscillate about a place of y equals 0, not x is equal to 0, right? So it's got to be really clear that our position functions are defined in different ways. The position function for any simple harmonic motion must be about the stable equilibrium point. For a spring, the x equals 0 position is where the spring is at its natural length. But believe it or not, all these equations, even though there's both gravitational potential energy and spring potential energy, the whole thing has the same set of equations here, as long as we understand here that the A would be from this new equilibrium position down to that maximum length, or that mg over k value. The last thing I wanted to bring out with the simple harmonic oscillator, it's a weird thing that they often talk about for multiple choice, is what happens if I have two springs attached to it, like if I have this or if I have this, okay? So I'm not going to get into the math of it because it just gets annoying. All the equations are the same, except what we have here is an effective K. And the effective K in these conditions here is going to be just adding the two Ks of the spring, because both of these springs are cooperating with each other, right? This one here also is cooperating with that one. If I smush this one, I stretch that one, they're both trying to getting it back to this equilibrium position. So this is often called springs in parallel, right? Because the two springs are parallel to one another. In this organization, and that's K effective. And there's a weird thing you can do, which is I can attach one spring to the end of a second spring, and here it's bizarre, right? Because the amount by which I stretch this or compress this is not the same by which I stretch this. This is called having your springs in series, and just because it comes up every now and again, the effective K for this is actually 1 over K1 plus 1 over K2, right? So putting your springs in series, actually the effective K decreases. Here, putting your springs in parallel, the effective K increases. So that is everything you need to know about the simple harmonic oscillator. You want to know these equations, know what they mean, because they just solve multiple choice questions really quickly, as well as know the understanding of what's happening change-wise throughout the cycle. And in the next video, we'll explore the rest of simple harmonic oscillator or simple harmonic motion and show you the other two types of oscillators that they use and the comparisons that they're going to draw from for multiple choice questions.